My pleasure to welcome everyone back for the last session of the workshop. Our first speaker is David Choi.
Thank you everyone for staying for the last session. So I'm going to talk about two projects. I'll go over them a little bit more briefly, and then I'll be here until the end of the month, so if you have questions, please feel free to chat with me afterwards. So the first one is co-clustering of non-smooth bipartite graphons. And so just the motivation is that we have a lot of results that exist for recovering the true communities of a block model. We understand that very well. However, in real data, the assumption of a block model, or even just assuming that there are true communities that you can recover, is probably unrealistic and doesn't really match current practice. I think actual practice is a little bit different than recovery. It's often we're trying to just explore or visualize the data set in hopes, as opposed to actual estimation or recovery of something that we believe to be true. So in that sense, I think when we use block model or do community detection, it's sort of similar to like using a histogram. Even where, if the underlying density is smooth, you can get very nice results saying how quickly you learn it. But even if the density is very non-smooth and very spiky, the histogram is still useful for exploring and visualizing and understanding the data set. And so my result is only going to apply to bipartite networks. Unfortunately for now, it's just a defect of the result. And so an example of a bipartite network might be people and then movies and which people like which movies. And my generative model is going to be a bipartite graphon. And so to generate from this model, it'll just be for each row and each column, you're going to generate a latent variable, just like it's just a graphon but in the bipartite setting. And so that'll be between 0 and 1. You'll look up that entry for each ij. You'll look up that entry in the graphon function, and then they'll give you a matrix of probabilities, and then you'll generate the aij matrix with those probabilities independent Bernoulli. And so this function here represents the population level network, and it doesn't need to be smooth or have any simple form. And in fact, to be realistic, you probably wouldn't want to make any assumptions on it at all if possible. And so we're going to do block modeling. And so just informally speaking, block modeling means you have some matrix. And then we're going to do this is a bipartite graph, so we're going to arrange both the rows and columns into separate clusters. And then, there are many algorithms that work well, and so they tend to find patterns like this where you say, well, this is a group of people, and they happen to not like this group of movies, but they like the other two, and then the opposite for this other group of people, and things like that. And so our question is going to be, what happens if you block model a network that was generated from a non-smooth graphon? And so Harry talked about some strong results, and so what's recently been shown is that you can find their minimax rates are known for estimating the underlying probabilities for the matrix that you drew, and then for estimating the entire function if it's smooth. And that applies for both bipartite and symmetric networks. And so in this talk, we're not going to estimate it because we're not going to have enough assumptions to do consistent estimation. We're just going to try to approximate a non-smooth omega bi block model. I put approximation in quotes because I need to make that a little bit more precise in 2 slides. And it'll be just for the bipartite case here. And so just as motivation, so why assume non-smooth graphons? So these are kind of harder to work with. And so just to give you 3 reasons. So first of all, unlike like image data or signal data where a lot of nonparametrics is commonly used, it's very hard to justify the smoothness assumption. You can't sort of look at the data and say, well, I do believe it looks like a smooth signal plus noise. And so networks are fundamentally different from those other settings in that respect. You might believe that omega is smooth in only a very high dimensional latent space where all of us have some latent coordinate, but it's very high dimensional. Maybe it's too high, it's high enough that you don't believe you could ever, you have enough samples to really exploit that sort of smoothness. And then finally, there's a very fundamental theorem, the Aldous-Hoover theorem, and it requires it to hold. And so here's my picture of the result of the sense in which I mean that we can approximate these non-smooth graphons. And so I'll just start with a data matrix. This data matrix we're going to say is generated from a graphon. Let's just say it's people and movies because it's easier and more fun to be concrete just for a conversation. And so we have this data set, which people like which movies. We're going to do some kind of exploratory bi-clustering, which means we'll use some algorithm, which we don't need to specify for the results of this talk to hold. And it's going to give you cluster labels. So S will map the rows to clusters. T will map the columns to clusters. And so here are the rows for which the cluster is 1. Here are the columns for which the cluster is 1. And usually these algorithms try to find things where some blocks are very dense, some blocks are very sparse. And so you might interpret these blocks. You might say, oh, you might look at the movies and you might find, oh, these are mostly science fiction movies and these are romantic comedies. And you might say, oh, it looks like our customers tend to not like both romantic science fiction movies at the same time. So let's not make any movies like that or something like that. So. And then so so the inferential question might be, well, that just happens to be the data you saw in your small data set, but what you really care about is the underlying population. And so this might be your entire market of the UK or whatever, and then this might be a conceptual population of the movies you expect to see in the future as well. And so you want your conclusion to not only hold for this data, but to hold for the population, because otherwise it's not a valid inference. And maybe then you should make movies that are both of both genres or things like that. And so you saw this pattern in your data, but for all you know, maybe this is actually just uniform Erdős-Rényi, and you just got an unlucky sample. And so that's the question we're going to address in this talk. And so what we're going to show is we're going to answer the question: wait, maybe does there exist? So in here, the underlying population is just some bigger matrix that we've sampled from with capital M and N rows, and it's just we're not making any assumptions on this form. It's just some arbitrary population matrix. And so we're going to ask if there exists clusterings of the bigger population that extend the data. And so sigma will extend S, tau will extend T. And so here I'm saying, well, here we ask, does there exist a clustering so that if we put the unobserved rows in these clusters like this, then maybe we get the same pattern that we saw originally in the data, in which sense we're saying, what we saw in the data does tell us something valid about the underlying population. And so here we're saying that, so this would be the people in the population in group 1, the people in the population in group 2. And so this is what, do the new people like these movies the same way that the old people do? And in which case, they would be science fiction fans just like these or something like that. And then we have another block for the new people and the new movies here, saying that, well, there's going to be a segment of the population that happens to like these movies a lot, but not these. And then there's another segment that likes these, but not these. In addition, these people also like these movies, so they have the same interpretation of being science fiction fans or whatever it is that you assign to it. And so in the picture, I represent the population as a large matrix with capital M rows and columns. But in the actual result, the population will be a graphon, the graphon I talked about. And that's equivalent in a rigorous sense to taking the limit of this matrix as the number of rows and columns goes to infinity. And so now these mappings of the population that we just want to know if they exist or not, they map 0 to 1 to different blocks here. And so just to draw that again, and to show the notation of what I need to describe to say the theorem. And so here we have, this is the people in the population. What do they think about the movies in the data? And so, wait, let's start with this one. So this is your data. And so it's this 0.8 density, it's the number of edges divided by the block size. So this phi A ST 1, 1 is going to be the number of edges in A induced by the clustering S and T for the 1, 1 block of it. And then we're going to divide it by the size of this cluster, which is the size of the first group in S and the size of the first group in T. And then likewise, you would have similar things for the other data blocks. Okay, and then so this block here will be the people in the population and how they think about the movies in the data. And so you'll have a similar summation of this omega integral over those quantities divided by the size of the blocks. And then this here is the integral of this here is just the integral of the graphon over the population in group 1 and the population in group 1 divided by the size of those blocks here. And so these are all analogous quantities. We want them to all be the same. And so we're going to control them in the theorem. We'll control the numerator and denominator separately. Okay, and so these are just the definitions again, the edge counts and the fractional sizes. And so the theorem is just that, so we just proved it for the rows and columns being comparable in size because it was simpler. And we said for every clustering of the data, there will exist a clustering of the population such that the edge counts are similar in Frobenius norm, and the edge class sizes the vector of class sizes are similar in Euclidean norm. That all is controlled by k squared over square root of n with an extra log term, which is probably loose, to be honest. And the constant factor in this omega the constant factor in this OP term is universal in omega. So we're basically saying that when you sample rows and columns from a bigger matrix, the sampling error goes down as 1 over square root of n here, irregardless of whatever community you take. Okay, so in my backup slides, I have a proof sketch, but I decided to skip over that to talk about another result. But I'm happy to show it if there's interest. So just some simulations. Here is a parameterized family of graphons. And so they're converging to a block model. So here you have 2 blocks, and the red is high probability, blue is low probability. here it's not really a block model because things are varying much more smoothly. And so I just wanted to show show that the bound is pretty good for across the family. So it turns out that these block models, these graphons, are all rank 2. And so for this thing here, I actually can evaluate these quantities over the overall rows and columns because it's low rank, it turns out. And so, so here's one of the terms that we're controlling here. It's the people in the population, but the movies in the data set, and then compared to the people in the data set, movies in the data set. And so if this is for larger n, for different values of beta going from smooth to block model. And so they all really do seem to follow this square root of n rate here. It seems like the result is pretty good here, up to the log. The log is probably incorrect. And so I think I'm doing, so that's all I was going to say about this project. I do have a little bit of the proof sketch. There's like a geometric argument that we use to bound things, but I'm going to skip over that and just talk about a second project instead. And so this project here is semi-definite programs for non-assortative and other block models. And this one is not as mature as the other one. It's still work in progress here. And so just the motivation is that in community detection, there's been a lot of recent activity in seeing how semi-definite programs can be used to learn communities. And I think some of the motivation is because they've been able to come up with proofs showing performance bounds even in the sparse setting, that even if it's constant degree, but not actually all the way up to the theoretical threshold, they're able to show that semi-definite programs still do okay, or they don't fail catastrophically. And also, more recently, there have been some possible connections to non-convex optimization. And so people have looked at taking these combinatorial problems, relaxing them to semi-definite programs, which are convex but actually pretty slow, and then trying to solve that semi-definite program using a non-convex relaxation, non-convex heuristic again, because it's faster, and then coming up with theory that says this whole thing actually works. And so it'd be interesting if we could, and those are two interesting things. One thing is that these STPs, they're all, in the literature, they're all for community detection. So community detection means the block model has diagonally dominant blocks. So if you're in the same community, you're more likely to talk to each other as opposed to different communities. But block models can model other things as well. And in fact, in some sense, you could think of them as piecewise constant approximations to arbitrary graphons. And so it'd be nice to be able to use semi-definite programs for those cases as well. And so, I will describe the semi-definite program. I think there are just a few main things I want to that I want the audience to see. That it's the way it works is it takes the adjacency matrix and it makes it bigger by a factor of k. So that's the main thing I want to show here. And then that you can actually still compute it, solve the STP fairly quickly. Okay, so the thing we want to do is we want to choose the latent classes to minimize this squared error here, where this is the adjacency matrix. This is the probability given the block assignment, and then we want these to be close in Euclidean distance and squared error here. And so A is going to be generated from some block model where the parameter matrix P is known. And so that's not always the case. That's in statistics, that's almost never the case. But this is sort of a starting point for what I'm working on. You might think of it as maybe if you could solve it for known P, you could maybe alternate back and forth between estimating the labels and then estimating the parameter matrix P, or some other ideas that are maybe further down the road. And so for now, I'm going to assume that the parameter matrix is known. So it's known how likely each group is to connect to each other. And there'll be this density parameter that we allow to go to 0. And so the only task is just to learn the unknown labels to say which nodes are in which class. So P doesn't need to, in this talk, P won't have to be community structure. So it could be just, the form of P could be as some density parameter times a matrix theta. And theta could be the identity plus a constant. So that means if you're in the same block, you have one probability. If you're in different blocks, you have a different probability. If this constant, if C1 is greater than 0, it's assortative, which is the case that has been done in all the other examples. You might have that plus maybe an additional peripheral class saying, well, most of the people are in communities, but then there's this other catch-all class that is people who are just sort of on the periphery. They don't really have any strong connections to anyone or something like that. That's something that could be useful in practice as well. You might have a hierarchical structure. So you might say, well, this theta matrix encodes hierarchical clustering. So maybe you have 2 to the L leaves. So there's L levels. So here there's 8 different classes. The probability that class 1 connects to class 2 is going to be some function of the tree distance. So here, the tree distance is close for class 1 and class 2, but is far for class 1 and class 5, for example. And that would be like hierarchical clustering. And then you could also maybe, for another example, might be some sort of latent space model. So you might say, so in this case, I'm going to say that your classes are points on the hypercube, and then the probability that two classes are connected depends on the Hamming distance between them. So how many bits do you share in common? So each bit might be one hobby that you have or don't have, and then your similarity across these bits determines your connection. Okay, so here's the STP relaxation. So the original problem is we want to choose the z's so that the p's are as close to the a's here. And so this term here, I'm just going to write as, you can write it as a generic function, and there'll be one function, such function for every dyad that you're trying to use. And so it's going to be a sum of these little functions here. These functions here, they take classes. So if you're in class 1 and then the other person is in class 2, that gives you like a certain risk and so forth. And so you can think of these functions as k by k matrices. So each one encodes all k-squared possible combinations of classes. And so you could think of this as you have a k by k matrix multiplied by two vectors, which are indicator functions that just pick out the appropriate element from that matrix. So that's one way to think of this function here. And then you want to say, well, I want to evaluate that sort of matrix product across all n squared of them at once. And so you can write that as a big matrix here. So this here is, so capital F is not n by n, it's not k by k, it's nk times nk. So each one of these is a k by k matrix for a dyad. And then you're putting them all into a very big block matrix. And then this here is nk. So each one of these is a k-dimensional vector saying which class that node belongs to. You encode them as a big vector here. And so then if you take the matrix product of x transpose fx, that gives you, that's the same thing as evaluating this summation right here. And so you can write that as a matrix inner product like this. So capital F, and then you have this big, so it's a big matrix here. There are nk entries. And this here is the original problem, so it's combinatorially hard. So this is a binary vector still, so it's still hard. And then we have this constraint saying that each one of these subvectors has to have exactly 1, 1, saying which class that node was assigned to. And so you can express the original problem as something that almost looks like a semi-definite program. And then you would say, well, let's do the semi-definite relaxation and just relax this to a positive definite matrix here. And so that's this. So here we've relaxed xx transpose to just be some matrix, which is positive definite. It has to be non-negative because it's the product of these binary variables. And then and then we're going to add linear constraints that capture the same thing as saying the sum for each of these subvectors has to be 1. So that means the sum for each of these submatrices has to be 1 because it's the product of two indicator vectors. And additionally, the diagonal blocks are an indicator vector by itself times itself. So that means the diagonal has to actually sum to 1 there because class A, node I cannot be in class 2 and class 3 at the same time. It has to be in the same class. Well, AA, yeah. So okay, so that's this semi-definite program. You can interpret it as, so the output will be this big matrix with nk times nk entries, lots of little submatrices, 1 for each dyad. You could interpret each of these submatrices is k by k and it sums to 1. So you could think of it as soft assignment of those two pairs of nodes, saying that for this block here was 1 in class 1 and n in class 3 or whatever. And then so that one issue is that these matrices may not be consistent with each other, but this is one way to interpret it. Okay, so I have a theorem for this SBM. So let's assume that the data is generated from a stochastic block model with known p, because we need that for our STP. And then we're going to have the density, the average degree will go to infinity, but can go to infinity arbitrarily slowly. So I'm not at the sparse threshold, but I'm in the semi-sparse case, I guess. And then the other parameter is fixed. We're going to solve this STP, and then so it's going to converge to something which is a little hard to interpret, but it's sort of like the true solution. And so we're going to say what happened. Well, let's suppose what would happen if we solved the STP, but instead of this noisy matrix A, we're able to replace it with the true probabilities P. So that squared error is just you see the probability of IJ, so just choose the classes that match that probability. And so unfortunately, there are many such classes because of label switching, and since it's a convex problem, all such convex combinations will have the same objective. And so there's a set of solutions that all achieve the optimal solution here. And so the one norm difference between your thing and that true solution is going to be a vanishing fraction of square root of n. So it puts vanishing error on the wrong dyad. So if two dyads are in the same class, in a regular stochastic block model, you're going to put vanishing probability on the dyad on the entries that would suggest that they're in different classes. The proof is really similar to the Grothendieck inequality paper that was recently published by Verschinen and Guida. And so here's a simulation to just give a sense of what the output looks like. So here is a pretty easy hierarchical block model where it's kind of dense. Here's the tree again. And so if you run the semi-definite program on this, you get this big NK by NK matrix with all these little submatrices, one for each entry. And so for each submatrix sort of gives a soft assignment to what that dyad, how that dyad was assigned. And so you could say, well, how much weight did it put on each ij having a tree distance of 3? And then so you sum those entries of x and you say, oh, it looks like these dyads here have a lot of weight on their being assigned to classes which had the furthest tree distance. And so we don't know whether this is class 1 and this is class 5, or this is class 8 and this is class 2, because that's not identifiable. But we can identify that these nodes are in a completely different branch than these nodes here. And then you could also look at the other entries of the x squared of this x hat matrix, and you could say, okay, it looks like these dyads here were tree distance 2. So these must have been in one branch, and then these nodes here must have been in the adjacent 2 pairs here. And then for tree distance 1 and tree distance 0, you can see it's a lot noisier because it's a little bit harder to tell from there's not as much signal to noise ratio here. But it's still sort of getting the right sense that, the nodes that should be in the same class are sort of being assigned more weight than it being in different classes. And so the output of this is quite different from the regular STP that we usually have. And we needed to do this to have non-assortativity and arbitrary probability P matrices, basically. So if you take these distances, you could imagine just doing something fairly heuristic to recover a good guess for the actual label, saying, well, these guys and nodes 1 through 300 must be in the opposite branch as nodes 300 to 600 and so forth. And then these would be a little harder. What I did is I took all of these matrices and made them into one big fat matrix. I did spectral clustering on that base, and then and it did a really good job. So here is the true theta, the true tree distances between the labels. Here are the tree distances between the labels that I estimated in that matter. And you can see they're pretty good. They're a little bit messy when you try to distinguish between adjacent leaves, but otherwise they seem to do pretty good here. Here's just one more example. And so this is a latent space model on a 3-dimensional hypercube, and then I made it non-assortative. So the closer you are in Hamming distance, the less likely you are to be connected. That's not very realistic, but I just want to show that the STP works okay for non-assortative problems. And so here you can run the STP, and it says, well, okay, so these are the nodes which I think are have the same coordinates in the hypercube. These pairs had opposite distances, so they were on opposite corners of the hypercube. These pairs had distance 1 and distance 2. And again, you could do you could put them into a big fat matrix, do spectral clustering, and then I think I had to do one more thing by hand just but then after, and I'll go into that if you guys want. And then so here are the Hamming distances of the estimated classes compared to Hamming distances of true classes, and they're fairly good, although you can see there are errors here as well. So the very last thing I want to say about this is that this is a semi-definite program, but the matrices are much larger. Instead of being n by n, they're nk times nk. So if you use ADMM, the bottleneck is that this ADMM step requires a eigenvector computation. So that's going to be nk cubed. So like if k is 10, that means it's a factor of 1,000 times slower than a regular STP, which is really bad. And so it turns out that if theta is structured, like these structured examples I've given, there are actually tricks to speed up the diagonalization. The matrices have a special form. And so it turns out for like this identity plus constant, it turns out that regardless of k, in order to evaluate the ADMM steps, you just have to do 2 diagonalizations of an n by n matrix, which is a lot better than n cubed than nk, diagonalizing one nk by nk matrix. For the hierarchical block model, the number of diagonalizations is the number of levels, so that's logarithmic in the number of classes. For the Hamming distance, the number of diagonalizations you need to do is the dimension, which is again logarithmic in the classes. And so it is harder than doing just a regular STP, but it's not exponentially so or anything particularly bad like that.
In the first case, you can just diagonalize explicitly, right?
No, you cannot. It's an nk by nk matrix, and then it's a big matrix, and each of the submatrices has. So the big matrix does not have this form. It's composed of n squared different little submatrices which all have this form, but with different coefficients for A and B. Yeah. So so dyads which are same class will have a large A. Dyads which are in different classes will have a large B, ideally. And so in these cases, what happens is that your x your submatrices are a soft assignment of what dyads you think they're in. And so, for example, in this case right here, if you're in the same class, you would say that there would be a lot of weight on the main diagonal. And you might not be, you wouldn't know which entry of the main diagonal because of label switching. If they're in different classes, you would want there to be a lot of weight in the off diagonal here. And so it turns out that every single submatrix will have this structure here, but with different coefficients. It turns out if that's the case, then all these submatrices will have the same set of eigenvectors. If they all have the same set of eigenvectors, you can actually write out X as this Kronecker product decomposition, where you decompose it into K orthogonal matrices. And each of these, to diagonalize, you actually just have to orthogonalize this n by n matrix, which is the eigenvalue corresponding to each of the n squared eigenvectors, n squared submatrices. And so you can just, it's like these are gory details, but it turns out that there are ways that you can diagonalize these things very efficiently because they have this nice structure here. And so you just have to diagonalize one matrix for each eigenvalue. If they're repeated eigenvalues, then you don't have to do it twice. So that's all I want to say about this STP. It's work in progress. In my simulations so far, to be honest, FTP and spectral clustering, they've actually performed comparably. I haven't done anything where spectral clustering fails catastrophically. That would probably happen when you do really large sparse cases. I haven't done that yet because I've been more interested in trying to find ways to make the numerical optimization go faster for different kinds of problems and stuff like that. So this is to be continued. It's work in progress. So that's it.
Thank you. Questions or comments?
Maybe I missed this in the beginning, but in your biclustering, are you constrained to have the same number of clusters in rows and columns?
My result is written that way, but it's not necessary. I could have done it with different classes, and then well, it's just a consistency result that holds for every clustering. So it's agnostic to the algorithm, I guess. Yeah.
Other questions?
No, same result.